was in here right now, counting him.
Can you all hear me okay? Thumbs up, any indication?
Yeah. Yep.
All right, thank you very much. This is the first time I've done a Zoom meeting with this class, so I want to make sure. If you can turn on your cameras, it helps me, but you don't have to by any standard. I've got to just set up one thing. Give me 1 second. I've been busy with all sorts of things going on today. Let me see.
Thank you.
Try to get my camera going right now. Give me 1 second, guys. There we go. All right. Okay, I think we got. Let me. First time on this is always kind of weird. Give me 1 second. Okay, I'm going to share a screen. Okay. Hang on. If I can. I want to make sure. Can you all see a a yellow tablet right now, class?
Yes, sir.
All right, you can turn on your mics. You can turn on your cameras if you're okay with it. You don't have to. And I got a couple of announcements. First thing, if I can get this thing to work. Let's see. You don't have to, though. Hi. Okay. You can, can you all hear me? I think you have thumbs up. If you want to turn on your cameras, it's fine. But if you don't, you don't have to. I appreciate, Ben. Appreciate anybody that does it because it helps me get a better read on the class and how they're understanding. Now, first thing, anybody that feels you're in any way, shape, or form under the weather, please go get tested if you're on campus. You can go to the health center over there. It's a drive-through. Trying to think of the name of the place. It's off of Donahue. I can't think of it. You can look it up. I can put a link for this stuff. So if anybody feels sick, and the reason I'm saying this, I want to be completely frank with you. Yesterday, I had a headache. I felt a little congested, and I didn't want to expose any of you to anything that could be problematic. So that's one of the reasons I went Zoom. There's a few others. I want to try this one time. Are you all together with me? Now, next thing I want to do is answer any questions you have about the homework or anything else first thing, because I gave you some homework. It was based in large part on the lecture material and some of the reading, right? It had to do with intrinsic impedance, E field, correct, class? Did anybody have any? Jack or Ashlyn or Tyler, anybody?
I have a question.
Yeah. This is Tyler, right? Tyler?
Problem 6.7, it asks,
Give me 1
yes,
second.
sir.
Let me get it and I'll show everybody. Problems, he's saying, if you can't hear him, problem 6.7. It's been a while since I've done this, guys. So if you got suggestions, let me know. 6.7. So let me get it up here for everybody. I'm going to show you in the book and hopefully you can all see that. Let me focus this too. I don't know why the focus is, where's that focus thing? Ah, there we go. See, autofocus I'm not a fan of. Let me get rid of that. Okay, give me 1 second. I'll tell you why. It keeps on unfocusing all the time. So 6.7, can you all see that okay? Everyone? Suppose E, and E is defined as pi times 10 to the 6t minus, and then it has two vector components. So your question's probably, it's not just beta z, right? It's got x and y. Is that it? First,
sir.
you all see the problem. I'm going to rewrite it, but this is a fundamental question. It's like, hey, it's not beta z, it's really a combination. So let me show you how to deal with this. First, and this is a good problem. I provided you with the solutions, didn't I, class?
Yeah.
All right. So I have E here. This is not a good one. Is equal to 5. And then it's cosine. And this is going to be pi times 10 to the 6. T minus 3x plus 2y. And it's in the AZ direction. Okay, I didn't cover this, but this is interesting. Here's the problem. You're used to seeing E be given as simply a magnitude E naught cosine of omega t minus beta z, right? That's generally the way it is, and this would be a wave propagating in the plus z direction. Here, there's neither z nor a simple beta term. It's two coefficients of both x and y. You follow me? So here's how we deal with this. And I'm going to try to do this in a way that I hope all of you can understand. First, graphically, if you talk about this being x and this being y here, maybe I should do it there. I'll make this y and I'll make the origin right there. All right. If you come over and you have this really, I'm going to rewrite this term here. This really should be 5. And then I'm going to put cosine of, and I'm just going to write down omega is pi times 10 to the 6t. Now I'm going to use the term omega t here. And I'm going to put minus the quantity right there, 3x minus 2y. I'll tell you why I did that in a second. It is AZ, isn't it? It has to be. Yeah. The only thing I've done is rewritten that, and I factored out a negative sign for a reason. Does everybody see the only thing I've done is factor out of negative sign here. So I have minus the quantity 3x minus 2y, close quantity. Can you all read that okay, class? Yes, I mean, okay, here's why I'm doing it. Now I'm going to go over here and I say, well, if I have 3x and I have minus 2y, it would be, this would be minus 2. This is the actual point I'm talking about if both x and y are equal to 1. Do you all follow me? You'll see why in a second. Agreed? Now here's the thing. When you take a look at beta z, right? That z right there is really a coordinate that has to do with the vector direction of propagation. Does this make sense to everybody? It's the z direction. Do you all follow me? It was minus beta z actually in this argument right here. This has to do with the vector direction. Well, it's assuming it's going in the z direction. What if it's not going in neither z or x, but a combination of, say, x, y, and z? Then you have something like this. So the question is, what direction is this propagating in actually? You follow me, class? I'm sorry, I can't see the chat questions unless I don't even know how to do this exactly. Give me 1 second. I see questions in chat. Oh, never mind. All right. Y'all still can see the screen, right? This screen right here. The yellow screen. You can't see the yellow screen? Thank you. I took care of that problem. I was worried about that. You will be, hopefully. Okay? All right. Now, here's how you do this, and I'll try to be as clear as possible. This minus this quantity is like minus beta z, but here's the way you do it. First, you need a vector direction of propagation. Now, be with me on this one. All right. So what you end up doing to get the vector direction of propagation, you'll take the coefficients of x. All right. So you've got 3x, and then make it just ax. It's the coefficient. Minus 2y, ay really. It's going to be the coefficients y. I'm going to show you how to get the vector direction of propagation. I didn't last time, but I wanted you to take a look at this. And in his reading, if you've done it, he talks about this. You with me so far? Now, divide that by the square root of 3 squared plus 2 squared. In other words, the magnitude squared of them. Here, I'm going to get, well, 3 squared is 9, 2 squared is 4, so I get the square root of 13, don't I? Right? So I have 1 over the square root of 13 here. And then I have quantity 3x, minus 2ay. This is the vector direction of propagation. Please just hear me out on this one, because I know this gets a little confusing. How did you know that? Can you prove that? I can prove it, but the proof itself isn't going to be as valuable as understanding how to get it, and you'll see why in a second. So what I really did is take the vector or the coefficients in x and y. So I took really, normally they put these as just a sub x. I'll put it as, I took a sub x, no, it's capital actually, capital A sub x right here, ax, plus, and this would be a sub y, ay, and then I divide it by the magnitude of ax squared plus ay squared. And here what I'm doing is saying, once I put the minus sign in front here, when I have a wave that is E is equal to E naught cosine of omega t minus, and this is important, minus some quantity, doesn't matter what it is, minus the quantity ax times x plus ay times y plus az times z. And this can be in any direction. Actually, it can't be in a direction that's, this directional form has to be perpendicular to this propagation vector, but I'm going to leave that alone. So I'm not even going to put a direction. When you have this, to get the propagation direction of the wave, you factor out a minus sign and you're left with this. Then you put the AX coefficient as the coefficient here with AX, the unit vector next to it, AY, coefficient of this Y, unit vector next to it, and there would be a plus AZ here if there was one to get the vector of propagation. Now that, I'm going to stop for a second because that's a mouthful. Are you all with me on this, class? You see what I'm up to? Give me a show, some way of indicating understanding. And please try to work with me on this. Thank you, Ashlyn. Maybe because I said about half the class didn't say anything. Does anybody not understand what I'm saying? This is how you obtain the vector direction of propagation. You can think about it just from beta z, all right? If you want the vector direction of propagation, the minus sign's factored out, right? Take the coefficient of z, it's beta, right? The unit vector a sub p would be equal to beta az divided by magnitude of beta, which is beta. So it'd be az. Do y'all follow me? That's propagating az. If it was a plus sign here, right, then you would have to take a minus quantity minus beta z. Does that make sense? And what you'd find out is the vector direction of propagation would be minus z. This is how you find the vector direction of propagations in general. Okay? You okay with that, Tyler? All right, so for us, we know the vector direction of propagation would be this right here. It would be 3 over the square root of 13 ax minus 2 over the square root of 13 ay. Agreed? Now, did you look at the solutions I gave you, Tyler?
For the solutions, on my end, it did not show up for that particular question and the questions after. I don't know why.
Did anybody else look at the solutions and see a solution to this problem?
The solutions for 6.7 to 6.10 weren't showing up, at least for me too.
Anybody see them? Can't hear you. Who's speaking?
I think I have a solution for it in my files somewhere.
I mean, but did I send you it or not? Is it on OneNote? I don't even have OneNote up.
Well, the solutions for 6.1, 6.3, 6.5, they're on there, but the solutions for 6.7 and the rest, they didn't show up for some odd reason.
You know, this might have to do with the driver. Let me just see here for a second. That was supposed to be in a Word file. Give me a second here. Oh boy. Give me one second. I'm taking a look here, guys. That's 6.7, right? Oh, I got the solution here. What's going on? I'll show it to you if I can. Can you all see that or not? Class?
No, it doesn't look like that. I can post a picture in the chat of what ours look like.
This is on OneNote, isn't it?
Mhm.
I'm on OneNote. This is my, this is what's on OneNote on mine. It's not on your OneNote?
Ours has like little blocks.
Okay, I think I know the problem. It's called drivers. This is a block of stuff that has to, it does say there's a page conflict. It says William Shimon has a page, Tyler Kennard has a page conflict. I don't know if you can see this or not, but anyway, what I'll do is this, all right? If I turn it into a PDF, everybody can see it. All right, let me turn it into a PDF afterwards, all right, Tyler?
Yes, sir. Thank you.
Sure. Let me get to this problem though. So that's the way you get the unit vector in the direction of propagation. And the way you get beta, let me get to this now. The way you get beta, this is the unit vector in the direction of propagation right here. And the way you get v beta that weighs this vector, because now when you take this right here, like, I mean, these terms right here, the beta that goes along with that would be equal to the square root of ax squared plus ay squared. Or it would be simply square root of 3 squared plus 2 squared, which is square root of 13. That would be the beta. You follow me, class? Tyler? You with me? Are you with me, guys?
Yes,
Ben,
sir.
can you see that? I just took the coefficients right here of I took the coefficients of x and y, squared them, and then took the square root. That is the beta. This is the direct unit vector in the direction of propagation is right here. Got me on that, Ben? All right. So I know beta, I know the direction of propagation. I have an expression for the actual wave propagating. I've got everything I need. Let me ask you this, and I'll get to the problem in a second, but this is exposing a lot of truth here. So if I wanted the phase velocity in that region, how do I get it? Can anybody tell me? Do you remember me doing phase velocity last time, guys? How many do? What's the fundamental for phase velocity? Remember I put the
omega over beta?
cosine equal to 0 and then 2 pi, right? Or excuse, I'm sorry, go ahead, say it. I'm wrong.
Is it omega over beta?
Absolutely. That's the fundamental. Phase velocity is equal to omega over beta. What is beta for that problem?
Square root of 13.
Yeah. But I should say omega. Omega, it's pi times 10 to the 6, isn't it, class? So it'd be pi times 10 to the 6 is omega, and beta is absolutely right, square root of 13. What does that come down to? Anybody tell me? I don't have my cat. You know, I use Octave. I don't use MATLAB for free. How many know what Octave is here, guys? I would recommend it because it's free and it does everything that MATLAB does pretty much, a little slower. So I've got Octave up there and I hope you can see it. So I'm going to find V phase for this problem is omega, which is pi times 10 to the 6th, right? And then it's divided by square root of 13. Well, 13 to the 0.5 power. I hope that works. So I got that as the phase velocity. Anybody confirm that? Oh, you know what? That ain't right. I don't think. Pi times 10 to the 6 and beta would be equal to that's what I got. Did you guys get that?
I got.
Now, in the solutions manual, Jack, you have it open? Or
Yeah,
is the solution, did they ask for beta in this one or no? Find the direction, we found the direction of propagation. And if we wanted, do you agree, is that the direction of propagation they gave, Jack, right here? I suppose I can look myself. Hold on. I didn't see, he worked out the square root. I don't know if you can see it or not, but that's 0.83 AX minus 0.55 AY, I think. I think that's going to be right once you do the square root business. You confirm that, Jack, or not?
yeah, it's right.
Okay. That's how you get the direction of propagation. The way he's doing it, I didn't spend time on this because we haven't got the power equation. But if you take E cross H, do you see this in the solutions here, class? Can you see this, what I'm pointing out? If you take E cross H and divide it by the magnitude of E cross H, that's the formal way you get the direction of propagation that he has in his book. The way I showed you is the way that advanced EMAG people do it. They just look at the coefficients of X, Y, and Z, and they make sure there's a minus sign out in front of that. Do you all hear me? It's easier than doing it this way. But let's go ahead and get H. It shows you H here. if we have E here in 6, 7, let me just show you what I'm going to do. I'm going to take this. Well, he does it right here. He turns it into a phasor, but I want to do it because this is a pretty good problem. Let me go ahead and do it on my own here. And I hope everybody can see this. This one problem is rich with everything I wanted to teach today. It's actually doing things for me, so I appreciate the question, Todd. All right, now we had an E field in general. Our E field was equal to 5 times cosine of omega t minus, and this is going to be 3x. And then it's going to be minus 2y, right? And it's in the AZ direction. That's the form given by Wentworth. Here's what the phasor form of this is. When I take E phasor, the magnitude will be the same. Please watch this. Now we're going to phasor domain, and I put a little squiggly over the top to indicate phasor. Y'all with me? Now, next thing you do, it becomes E to the J, but here you put a minus sign there. You see this minus sign? That goes there. Y'all see that? I'm literally taking it. I'm not sure this was ever taught to you, but the way you turn a time varying wave phenomenon into a phasor, omega gets suppressed, omega t completely. You're going to take the magnitude here. It would be E. That, if that was a plus sign, it would be plus here. If it's a minus, it's a minus. Now the quantity here, these coefficients, I mean, not coefficients, this expression comes right up here. So it would be 3x minus 2y, and then AZ. That's an expression for the electric field phasor quantity. In his book and in the solution, what he does is this. He'll leave it as 5, and he'll break this up into e to the minus j 3x, or you can do it this way, and then it'll be e to the j 2y AZ. Y'all follow me? I just broke up the exponential. Now here's something. Some of you are bright enough to say, well, you don't even have to put that minus sign. Why don't you just take the coefficient of the, you take the coefficient of the 3 and put the minus sign in front here and just take the coefficient of 3. Oh, that's not going to come out right. Take the coefficient of the minus 3x before I do this. But I always do it this way because that minus sign tells me right away that everything over here in the parentheses has to do with the actual direction of propagation, not negative the direction. That's the only reason I do it. Make sense? If you factor out the minus sign, you know that whatever's back here has to do with the direction of propagation when you get a unit vector associated with that XY coefficient business, okay? I realize what I'm saying to you may not be completely satisfying, but I'm doing my best with the time allotted. The real way you do it in Wentworth's book is E cross H over magnitude. The problem is, if you don't know the direction of propagation, you don't know H. So you got to get it one way or the other. This is the way. Now, hear me. If that's the E field, I didn't get to this yet, but I'm going to right now. There is a relationships that I want to show you that are in his book, and I didn't get to, but I wanted you to take this problem and try it for a very good reason, because the questions are formed in your mind. If you did the reading, you see how he, and looked at the solutions, you see how he did it. If you didn't, you're like Tyler, you were wondering, how in the world would you do that? So now you got the question that is going to be answered, and you retain it. Now, we got the vector direction of propagation right here, which is equal to 1 over the square root of 13, right? And then it's going to be 3ax minus 2ay. Just rewriting it, right? Here's something to consider. First, the way we find the direction of power flow that I didn't get to last time, this is the ultimate thing that shows you the direction of propagation. So please take a moment, write this down, call it power flow. And that's equal to P av, it's the average power density. And the fundamental definition of power flow in the time domain, call it P av here, but in the time domain, vector power flow, instantaneous power flow, is equal to the electric field, that's a vector quantity in the time domain, crossed with the magnetic field in the time domain. Both of these are vector quantities and they do vary spatially. Now I'll spend more time how to get them in a second, but this would be the instantaneous power flow. It would be like the instantaneous power that would be dissipated by an element, resistor, inductor, or capacitor, would be V times I. Do you remember that? V of T times I of T would be power. Do you all remember that, class? This is power density really flowing. The units of this are going to be watts per meter squared. And we don't generally use instantaneous power flow. Just like when you had your circuits courses, you talked about power. Have you had your power course yet or not?
Yes,
How many
sir.
have had power in here? Gross usually, right? You have? If you haven't had power, just hang with me. Power is almost always talked about in terms of an average power, not instantaneous for a lot of reasons. Average power means the power equivalent to what a battery would dissipate into the same thing. And that's the reason we use average power, DC source. So we talk about average power. Write this down. This is going to be the average power. And this is going to assume that we have a propagating wave. Again, average power is going to be 1/2 the real part of vector E cross vector H. But these are going to be phasors, and I'm putting a little tilde over them to indicate phasors. I want to make sure, can everybody hear me okay? And is the internet not dropping me at all? Correct? Yeah, and I may get some negative reviews, but if you could turn on your cameras, it helps me immensely. If you don't want to, it's perfectly fine. But can you all see what I'm seeing? Can you see a bunch of heads in yours or not? All right, it helps. I mean, some people, I understand when I'm real shabby and stuff unshaven, I don't want my face on there either, but it's helpful to me because I can see your expressions. All right, now this is something that gives you the average power flow. Well, that's a vector direction, isn't it? That power flow tells you the direction it propagates. However, to get this, you need E cross H. Do you see that? You need both E and H to find this. And this would be average power. It would be in watts per meter squared. Now, here's the thing. If we talk about just unit vectors, can you work with me on that? Unit vector is what? It has a magnitude of 1, correct, class? Doesn't have to be just AX, AY, AZ. It has to have a magnitude of 1. So if we talk about unit vectors, the way we talk about the vector direction associated with the propagation, it would be A sub P. P just means propagation, but it's got a magnitude of 1 and it's just in the direction of propagation. And please, if you have questions, if possible, unmute yourself, because sometimes I cannot see the questions when I share screens. And that's equal to, now listen, that's equal to A sub E. That's a unit vector in the direction of an E field crossed into A sub H. Now that's a unit vector in the direction of the H field. This is true. And you remember back in the day when you had, you didn't have vector calculus. I don't know if you had this. If I have this, I also know the vector direction AP is equal to minus AH crossed AE, right? If I just reverse the order of the cross, I get a minus sign. How many remember that? There you? Remember, if you reverse the order, if you have AX, think about this, unit vectors. What is AX crossed AY? Do you remember what that is, class? How many do? 1, 2, 3, 4. At least 4 that I'm talking. Well, the way I've always taught to do it is you use your right hand. I'm assuming everybody has a right hand. You take your index finger in your right hand, point it in the direction of the first vector, X. Do this on your, I don't know, whatever, wherever you're. Then you take the index finger, use your thumb, stick it straight up, use that as an axle, and rotate it into the second vector. So I have AX crossed AY. That's the resultant vector, which would be, if you think about X crossed Y, is Z. This is AZ. All right. Do you remember that? AX crossed AY is AZ. How many do? Okay, God, I'm so thankful. Thank you, guys. Now, if I reverse the order, if I have AY crossed into AX, do it with the right hand. AY, this is going to be upside down for me. AY crossed into AX is minus AZ. Follow me? You do it in yourself. So minus AZ. And what I'm really trying to tell you is this operation just puts a negative sign in front of the top, the above operation. Switch the order, you get a negative, all right? You good with that? Now here's the thing. If I go ahead and I do an iteration where I move, if I take everything and move it over one, if I take A sub P and put it over where E is, AE where AH, and then I would rotate AH back here. In other words, I would get AH, unit vector in the direction of the H field, would be equal to unit vector in the direction of propagation crossed into unit vector in the direction of the E field. You can do this. The way it's shown sometimes is AP, and then it would be AE, and then it would be AH, and then back this way, and you put a plus here. That's plus rotation. Do you remember this, by the way? What I think you were seeing is this when you were taught. It was AX, AY, AZ, and you had like this, arrow, arrow here, all plus. AX cross Y is AZ, AY cross AZ is AX, right? And AZ cross AX is AY. Do you all remember that? And then if you go the other way, if you go this way, right, you put a negative. So AZ crossed AY is minus AX, AY crossed AX is minus AZ, and so forth. You remember that, those little memory tools, right? Back to this thing. This is something people use all the time. But here's the real thing they use. What you want is AH, unit vector in the direction of the H field. That's A sub P, which I showed you how to get, crossed into AE, right? Now you have to have the unit vector in the direction of propagation to do most of this. So it's a catch-22 with Wentworth's problem. He didn't tell you how to get the H field's direction, and he asked you for the H field. Now, but I showed you how you get the unit vector, okay? You okay with that, everybody? I tried my best. Go
There
ahead.
was, I found the H field direction using Maxwell's equations and Faraday's law.
Yes,
So I
but
didn't.
that's a lot of work. I mean, this is me personally, as an engineer, the last thing we want to do is increase the amount of work we do. We got more than enough to keep us busy for the rest of our lives. So what we try to do is make it the most efficient, accurate way as possible. What I'm showing you is the quick way. You're absolutely right. You can take a curl of E, right? And you get minus what? J omega times mu times H. Yes, indeed. You're right, Jack. Do you want to do that all the time? I don't. It's a pain in the butt because you got two variables. So don't do it. What were you going to say, Tyler? You took your mask off. Don't say any vulgarities. Don't say anything, any nasty thing about anybody, especially me. No, it's like, all right, here we go. Let me show you the bottom line, and it's in Wentworth's book, I hope. It was there last time I looked, unless somebody found a way to cut pages out of my book. Yeah, here it is, guys. You ready for the goal? This is about 40% of the lectures, today's lecture. It's right here. It's on page 327. Can you all see that right there? It's E and H field in terms of each other. And you see how it's reliant on the unit vector in the direction of propagation. You all see that? Now I'm going to do that for this one. And William, are you recording this or not?
It says you're recording.
Yeah, I am, but this is going on Zoom. I can give you recording privileges. Why don't I just do that? Hold on for 1 second.
If you
Remind,
post it on Zoom, I should be able to download it.
really? I'm
Yeah,
gonna allow you to record too. I just
Okay.
allow, if you want to record it right now. If anybody else wants to record it, let me know. And I'll
Alright.
make it, because I encourage you to record it and put it on YouTube or make a copy for yourself, because remember this much. Zoom stuff will be rewritten over, all right? I got lectures on YouTube that are 10, 12 years ago of mine that students still refer to, and I prefer you have that, or put it on your own computer. Make a copy. I encourage that. Back to this thing. Now that I've showed you, I let the cat out of the bag. If you have your books, here's how we do it. We say that H in general, they wanted H, that's equal to 1 over the intrinsic impedance. I did cover the intrinsic impedance, didn't I, guys? Right? Yeah. 1 over the intrinsic impedance of the region. Then it's going to be a unit vector in the direction of propagation crossed into the E field. That's how you get the H field. We'll do that one. By the same token, if you have the H field and you want the E field, it would be equal to minus eta, that's the intrinsic impedance, times the unit vector in the direction of propagation crossed into the H field. Now these two are essential. And if you remind me, I'll provide those for you on a quiz. I don't usually do that, but I think until you get real familiar with it, I'm going to do that. Now, here we go. We had, for our case, we had the E field, that's the vector phasor form, was equal to 5, right, times e to the minus j. And I think it was 3, right? Was it 3? I'm trying to remember now. 3ax minus 2ay, right? Or 3x, pardon me, times e to the plus j2y az. Do you agree with that, everyone? Right? We have the unit vector of propagation equal to 1 over the square root of 13, and it's equal to plus 3ax minus 2ay. And now if we want h, this is the vector phasor point, I have 1 over eta. Does it say this is in what media? Let me just
It
tell you
doesn't
one.
really specify, but in my solutions, it says we assume it's non-magnetic.
It isn't, but I'm going to show you a few things. Can you all see this right here? I hope you can. Y'all see this right here? Now, is there an e to the minus alpha anything there? Is there e to the minus like 5z2y anything? No. All the you can see that there's no exponential decay, so it is lossless, number one. Do you all see that? And if it's lossless, the next thing we can do is find out what the value of mu and epsilon are. And he says non-magnetic. Are you ready to see how? All right, here's how. This problem has got everything in it and more. So we know that gamma is equal to the square root of j omega mu times sigma plus j omega epsilon. And that's equal to alpha plus j beta, right? Everybody? Now, it's lossless. There is no attenuation. So what that means is there is no sigma. With me? Sigma is a conductivity. It has to do with current flow and energy. Really, it's an energy. It's a transducer type effect. It takes electromagnetic current flowing and turns it into heat. There's nothing there that's going to cause loss. That means this term right here becomes just J beta, and that's equal to simply J omega times square root of mu epsilon for lossless. Do you follow me? This will bother some of you, but hang on there. So if that's the case, then we find out that beta, and write this down, this is for a lossless region, is equal to omega times square root of mu epsilon. Okay? Now, if beta is equal to this and it is non-magnetic, it means mu is mu zero. Agree? And I can say that this is equal to omega times square root of mu zero epsilon zero times square root of epsilon relative. And that's beta. Agree? And now I can find epsilon relative. I can say that epsilon relative, I'll square both sides. And I'm trying to find epsilon relative here. I got the square root of epsilon relative. Let me do it this way. I'll take square root of epsilon relative will be equal to beta over omega times square root of mu naught epsilon naught. Are you with me? I'm just rearranging. That's square root of epsilon relative. Now follow me on this. Beta is square root of 13, right? Omega is pi times 10 to the 6th. Does anybody remember what 1 over the square root of mu naught epsilon is? It's a very famous term. Anybody at all? Unmute yourself, please, if you're going to talk.
The propagation velocity.
Say that aloud. Say that again.
The propagation velocity.
Yeah, but there's a more fun. It's absolutely true. This is the speed of light, c. It's 3 times 10 to the 8th meters per second. It's an extremely important constant to know. And as an electrical engineer, if you're asked about it, you should respond very quickly. Are you with me? So it's the speed of light, but in a vacuum or in free space. And that is a constant in all reference frames. More on that later. It is an amazing fact. So that's the speed of light. What I mean to say is this right here, 1 over the square root of mu epsilon, I can just put down as 3 times 10 to the 8th on top. That's not exact, but it's very close. With me? The measured value is very, 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 very slightly off. Now, if you take a look, that's equal to the square root of epsilon relative, and that means I can find epsilon relative by squaring this. And what I'll do is cut it down a little. So if I take epsilon relative here and I square both sides, here I'm going to get 13, right? And then if I look at this, well, I have 10 to the 8th, 10 to the 6th. That's really 10 squared. If I square that, I have 10 to the 4th. And then I have 3 squared, or 9 over pi squared. And that would be epsilon relative. Do you agree with me? I feel the same way, Todd. Are you with me on this? Now, what's the value going to be? Anyone? Where's my octaves over here? I'm doing it in octave real quick. Times 9. Did you get a large number? Let's see what it says here. I think this problem is a goofy problem here because I'm getting a phase velocity that's orders and orders of magnitude. I got a value of about 118,000 for epsilon relative. Did y'all?
That's what I got. But then, so I did it two ways. I did it without squaring everything, and then I did it with squaring everything. And I think you have to take the square root of your final answer because you squared both sides. So that's your answer squared, I think.
No, this is epsilon relative though, right? Isn't this correct?
Your OneNote screen is in the way.
Oh, I'm so sorry. Yeah. If you look here, I'm sorry about that. This is true, right? This. You see it, Jack? That's true. So I'm after square root of epsilon relative. It would be beta over omega square root of epsilon mu naught epsilon relative. So beta is square root of 13, right? Omega is pi times 10 to the 6th, right?
Yeah, I see what you're doing now.
And then this square root of mu epsilon is 3 times 10 to the 8th up here, right? 10 to the 6th, 10 to the 8th is just 10 squared. Y'all agree with me? Take that quantity, that square root of epsilon relative. I need to square it. Square root of 13, 13. Square root, or square 3, get 9. 10 squared is 10 to the 4th. Pi squared. I get an answer that's huge. And I think Wentworth just created this problem. It's not based on anything physically realizable. Okay. So that's it. Nevertheless, we have to get eta, correct, class? This is what we need. What's eta going to be? And I'll put it here. Eta itself. Now let me write this down. Guys, I'm over by a minute. Now, I want to say this to the class. If you need to go, go. But now it's an office hour. Is that fair with everybody? This is the first whack at this, and it wasn't planned in advance. So if you need, how many have a class right after this one? Just show me. Could you give me some indication? Ashlyn, do you have one right now? What, Tyler, what time? Is it right after this?
I have work at BK at 1 o'clock.
Well, you got to go then, buddy, because it's 12:52. You got to go. But this recording will last. Anybody else have a class or a job or something like that? Nobody? Didn't somebody else have it? I wish you wouldn't put it in chat because this doesn't pop up for me. Can somebody tell me what's in chat? Just briefly. There's
nothing in chat.
Oh, excellent. All right. If you got to go, you got to go. But for eta, remember, I put it down. If you got to go, this will be available. All right. And I hopefully will be back in person. It'll be a lot better. But eta itself is J, right? Omega mu over sigma plus J omega epsilon. That's the general form, isn't it? Remember, if you don't remember it real well, just realize this is what I developed last time. Now, sigma was 0. That means eta for a lossless region, the J omegas cancel and you get the square root of mu over epsilon, or it's the square root of mu naught over epsilon naught times square root of mu relative over epsilon relative. Now, the only thing I'm doing here, and Tyler, I don't want to get you late for your job. So if you got to go, scram, really. I'm serious. All right.
Thank you.
Sure. But do y'all agree that that would be the case for a lossless media? Agreed, class? Now, look here. This square root of mu naught is a very famous constant. It's called the intrinsic impedance or characteristic of impedance of free space. It's termed eta naught, and it's really equal to 120 pi ohms, or about 377 ohms. So this equation, eta for a lossless region, is equal to 120 pi ohms times square root of mu relative over epsilon relative. In our case, epsilon relative is 1. I mean, mu relative is 1, but epsilon relative is huge. It's equal to 118,500. Matter of fact, let me do this. Let me go ahead and just take the square root of that because or I'll get epsilon relative itself here. For this one right here, you find that eta itself, you can't see this and I'll show you in a second, is equal to 120 pi times or divided by SQRT of epsilon relative. So I got eta of 1. Did you get that? And by the way, that's ridiculously small. You check me. I think that's the reason Whitworth did this. He chose eta as 1, and this is the result. Okay? So if eta is 1 here, then here's what happens. Now, we're going to just assume eta in our case is 1, which is extremely small. And what that tells you is what? When I go ahead and I get the H field, it's 1 over eta, 1 over 1, unit vector in the direction of propagation, right? Well, that's going to be equal to 1 over the square root of 13 times 3ax minus 2ay, right? Crossed into the E field. And the E field is in the AZ direction. Let me do this on the next page. Can you all hold on for 1 second? I hear people jumping off, but just bear with me. So if I do this, now I come out here and I get the H field as 1 over eta. Eta is 1. Unit vector in the direction of propagation, which is going to be 3ax minus 2ay over the square root of 13. And now this is crossed into the E field, which is 5e to the minus j 3x e to the plus j 2y az. And now I find the H field. Since eta is 1, it's equal to just 5 over the square root of 13 here. Then I take ax, right? And I have to cross it with az. And what's that going to be? X crossed z is, anybody? Minus ay, isn't it? Minus ay, right? And then it's going to be, and that's going to be times 3, by the way. And then I have minus 2ay crossed az. Well, yz is x, so it's going to be minus 2ax here. And then I have to put down the e to the minus j 3x times e to the j 2y. And that's the vector phasor for H. Right there. This coefficient should be out in front. Now, you all see right here, I've got coefficients in terms of x and y. Usually you take the coefficients out in front. But I have 2 components here, right? Y'all see that? The H field now has 2 vector components. And if you look at his answers, or once I give you the PDF of this, you're going to see something amazing. It does, in fact, have 2 components. And can I make this bigger? I think I can. If you look here, you see how this H field of his has 2 components? They're both negative out in front, the coefficients. Y'all see that? Let me make a final statement on this one. The vector direction of propagation is the same in the argument of the cosine internal to both of these will be the same when we go from phasor to time. Make sense? I know I'm taxing you a little. You with me? So the reason this problem, and I'm so glad Tyler asked about this, is essential is it identifies how to find a vector direction when you have both x and y, z coordinates involved in the argument of the cosine. It shows you also how to identify epsilon relative if it's lossless from beta. You can also get it from the phase velocity, but here I'm just wanted to do it the way I did it. It shows you this equation. I showed you the power, how to find power, right, class? How many are hanging on okay right now? Why don't you take a thank you, Ashlyn, and the guys with your cameras on, you okay, William? All right, and somebody had to go. I think Ben had to go. And as far as the rest of you, Lydia, Rafang, Logan, Connor, and Siko, are you guys okay right now?
Yeah, I'm good.
All right. Take a breath here because we're over. Now you have to understand, whenever I do lectures online like this, I assume a few technical glitches, things like that. I'm trying my best here to answer your questions in a timely way. But this problem is so rich in things, and I springboarded into power, right? Let me do one other thing with power. Are you ready? Just hang on. I know it's Friday. All right. And I know you got the weekend, but just hang on with me. Do we have a ball game by the basketball game this weekend or no? Anybody know? Is there any event this weekend besides the playoffs in the NFL that is overwhelmingly interesting to all? Nothing. All right, that's all right. And we don't have class Monday, do we? Or do we?
No class Monday.
Yeah, and that's the thing I didn't announce. No class, which is another good thing because I'm sure I'll feel better. So we can meet in person Wednesday, God willing. All right, follow me on this. So we're down to this point. Now, here's the thing about power. Please catch me on this one. And some of you are going to say, well, where does this come from? Let me ask you this. If I have an element in circuits, right? If I have a current I flowing through there, and it develops a voltage V across there.
Dr. Baginski, it's on your OneNote. We can't see what you're writing right now.
You know, thank you. I got to be more cognizant of the fact that this is, if I have I going in here, and this is a voltage V, and this is some unknown element. Now, you all have had circuits, and you probably work with this stuff more than just circuits, right? If I have this, what is the power associated, average power, from Gross's class or from circuits or from any of those things? What's power always going to be?
IV.
That's V times I in general, right? No vector direction. That's sort of true. This is not quite true. What's the real way to do it? If you wanted average power, it would be 1/2, right? Then would be the real part of V times I conjugated. Do you remember that from Gross's course or any of that? It's V times I conjugate. And the 1/2 comes in because the V and the I are peak quantities, not RMS quantities. Remember that, guys? The units of power are watts, aren't they? Now, when we are talking about average power, we're talking about electric fields, the power itself will be in watts, but it'll be a density, so it'll be per meter squared. So when we talk about the average power flowing, and this is true for a propagating wave, it would be 1/2 the real part of the vector component of E cross the vector component of H vector conjugated. Now this will give you the vector of propagation as well. E cross H will be in the direction of propagation, but be weighted by a big constant. So this is how you get the average power. Now I'm going to take it and make it easy to do. If you go ahead and put in E, remember H and E are intimately linked. You can't separate them. You have an E field that's linked to the H field for the propagating wave. Are you with me on this, class? This is not near field phenomenology. We're talking about a launch propagating wave. When you do this and turn the crank, I usually do this in class. I'm not going to do it here because I'm already over, but this is an office hour. You get 1/2 the magnitude of the E field. This is a nice formula to remember and use. And then you have the magnitude of eta, because eta itself could have an imaginary component. Then you have e to the minus 2 alpha z, and this is assuming it's propagating in the z direction. So I want to tell you, I'm using this out of Wentworth's book. And in general, I don't give you any problems where energy is propagating in like an X and a Y direction, like problem 6, 7. I would not ask you for the power. I could related to that because it gets a little hairy right now and you're just being introduced to it. So I'm assuming the E field's propagating the Z direction here, just like his book does. And then it would be the cosine of the angle, phase angle associated with eta. Now it's important you understand that phase angle has to do with the angle associated with the intrinsic impedance. And then it would be in a unit vector or in the direction of propagation. That would be the average power flow. I'll do that again, but I wanted you to have that, and here's why. What I'm going to do next time is talk about sections 6.2, 6.3, and 6.4. All these are linked together. Dielectrics, good conductors, and charge-free media, and even 6.5, the Poynting theorem. This is what I'm showing you is called the Poynting vector theorem. And I think I'm going to do a lot more problems that'll be simpler, but I'm going to go through this next time. And really at this point, I know we spent a lot of time on that one problem, but it was so valuable to do because it answers so many questions. This is in your book, and I'll give you the page number. Let me show you this. On page 344 here, you can see what I put down earlier. Then I want to show you the real one. Here, that's the formula I just put down. You see how he has P av equal to magnitude of E squared over magnitude of eta minus 2 alpha Z cosine of the angle associated with eta in the AZ direction. Here he's assuming it's propagating in the AZ direction, and the E field has only an X component. We can open that up and we can make it more general, but this for now is good enough. And he got it from doing E cross H conjugate right here. Everybody see that okay? And thank you for hanging on this long, guys, really seriously. Now, what I'm going to tell you about, polarization is easy. It's next there. And a lot of this stuff back here I'm going to cover. I'm going to give you a reading assignment this weekend, if you don't mind. I know you have Monday off, and I really don't like to be messing with holidays and homework, but I'm going to ask you to do a little bit for me, all right? Now, do you guys have any questions, comments? And did you understand the way I taught this lecture? Was it okay?
Reading the notes was a lot easier this way.
Did you like this way?
Yes.
Was it okay? Jack, was it okay for you?
Yeah, it was good. I mean, I kind of like, there's pros and cons to both, I guess.
I like being in person. I can see you for starters. Second, I can put boxed off equations in a corner and read from, go to them. And I can draw three-dimensional drawings and, sketches very easy. My handwriting's better to see, even though it's a rotten board. Ben, did you see this okay?
Yeah, I saw it okay. I'd say it was a little easier to see in this setup, but the other one was okay.
I appreciate
just some
that.
glare on the board and stuff.
Yeah. Maybe I'll work on my handwriting. I don't know what to do sometimes. Look, I want you all to stay safe this weekend. And here's one of the things I'm going to just level with you. Now, there are students that are positive that I'm finding out about. It's inevitable you're going to expose yourself to COVID just running around the halls. There's somebody around there that may have it. I'm not saying you're going to get it, but let's face it, in a campus this large, if you go to a grocery store, probably there's somebody in there that's got it, doesn't know they have it, or they're not saying. So what I'm going to say is, if you feel sick, ill, have a fever of any type, please go get tested. And if you would mind, inform me also if you happen to be one of the unlucky people that have this thing. And there's these regulations called HIPAA rules that are federal that prevent me from identifying a person or anything like that. But let's just go on the assumption that there's always people that's got COVID in your environment. So always be careful and do your best to stay away from people. By the way, William, are you up there in Brown or where are you?
Yes, I'm in Brown right now.
Crowded right now or not?
In between classes, yeah, it's pretty crowded.
All right. My advice to everybody is try to stay safe this weekend. I know it's very hard not to go into restaurants and bars and stuff like that and socialize, but at least for the first 2 weeks, try to let this thing die out. There's people that are positive. Last thing, I'll take, since this is my official and first office hour, I'll take any questions you have. They can, I mean, related to the course.
One I had in the reading that you assigned last time, it's on page 346 and then goes on to 347.
Okay, let me
For
show
Ju-
everybody because some people might not have their book. And I hope you can see it okay. This is 346 right here.
And it's the drill 6.9.
Okay. At the surface of a thick slab, we have an E field here. Determine, okay, E, H, and P. So he wants this. I'll show you what this has to do with. But first, if you look back here in the prior stuff, this is pointing vector and power transmission. So you guys you don't mind working through this or seeing how it's done, everybody? I got to show you a few things. All right, I'm trying to make sure everybody can see this okay. So here's the drill. I can blow this up if I need to. I hear people dropping off and I don't blame them. So we don't have a ball game then?
We do actually tomorrow against Kentucky.
Here or in Kentucky?
Let me.
Kentucky is the big, I mean, that's always the big game in the SEC is Kentucky. It doesn't matter if you're Tennessee or Alabama. They're the monster usually. With North Carolina, with Kentucky. Is Calipari still there or not?
Yeah, he did.
Yeah. We do have Bruce, so who knows? Maybe, is it here or not?
Yeah, it's here.
Let's take a look at this. Is a weird one, isn't it? Look what he gives you. He gives you an E field, at least the one I'm looking at here, is going to be equal to 10 times cosine of 3 pi times 10 to the 7th t ay. And he says that sigma is 10 to the minus 16th. Epsilon relative is 2.56. And it's for z greater than 0. Okay. He's saying that's what the field value is at z. He should say z equals 0. Here's the problem. This is at z equals 0. He doesn't state that in the problem. At least I don't see it. In the problem, he says, huh?
Top of the second page.
Is it there? It says
Yeah.
determine z for z greater than 0, but they
Oh,
don't
z.
say that that's at z equals 0. Oh, yeah, it does. It does. I'm sorry. So that's at z equals 0. So beta z doesn't appear, does it? Follow me, class? All right, but we can get beta. We can say if that's given, we can get beta. And we can get beta by a couple of ways. Well, if you look at this equation right here, he gives you these values. And what else does he say? Anything about mu? All right, look, here's how we do this problem. First, you all agree that omega for this problem would be 3 pi times 10 to the 7th. That would be omega. Agreed, class? By inspection, correct? Next thing when we look at this, if we have omega and we have these values, epsilon relative is 256. The next thing we can get is beta. First of all, when we look at beta, really what we do is look at gamma is equal to the square root of j omega mu times sigma plus j omega epsilon. Do y'all agree with that? Right? Can you see it, Ben? All right, now watch. If we have this, I'm just looking at something. If we have this, we can say gamma is equal to the square root. Remember, he identifies the material as polystyrene. So it's non-magnetic. I would be j omega. My omega is this. I'm going to leave it as omega times mu, which is mu naught. And mu naught here is equal to 4 pi times 10 to the minus 7th. The units would be henries per meter. Do you all remember 4 pi times 10 to the minus 7th is mu naught? Ashlyn, do you remember, did I teach you this, Ashlyn, or not?
So I know that I remember that from when I remember that from reading the textbook, but I don't remember. Yes, you did go over that on the 13th. You went over.
I don't remember if I went over it in class, but mu naught and epsilon naught are things that you had in EMAG 1, right?
Yes.
Yes.
Okay. All right. So I'm going to just leave it as this for now. It's 4 pi times 10 to the minus 7. Then it's times sigma. Sigma in this case is 10 to the minus 16. I know you want to get up and stretch, walk around. Go ahead if you want to. And then it's going to be plus j omega. Well, omega, I'm just going to leave as omega here. And epsilon. Epsilon relative is 2.56, right? So it's 2.56 times epsilon naught. You can do this. And you're going to get alpha plus j beta. You agree with me, everyone? We got all the values. We got mu naught, got omega, got this. Omega, got that, 2.56. Epsilon naught, I didn't put it down, but epsilon naught is equal to what? You can put 1 over 36 pi times 10 to the minus 9th if you want, but about 8.854 times 10 to the what? Minus 12th farads per meter. Go ahead, I'm sorry.
I was just going to say negative 12.
I couldn't hear you, William.
I was just going to say negative 12, but you
Yeah, you're right. You're with me on this? These are constants. They're universal constants. Now, so if that's the case, if I want alpha and beta for this, tell you what, I'm going to actually do this. This reminds me of a problem session that I had. I don't like these on Zoom. I like to be at the board. Let's see if I can get that here. I'm going to just use this, okay? So brought back my screen. I hope you all can see that. And this is, again, this is octave. So I'm going to put epsilon naught is equal to 8.854 times 10 to the minus 9th. And then, oops, sorry. Wrong thing, got to be equal. And then I'm going to say that mu naught is equal to 4 times pi times 1 e to the minus 7th. And let's see, what else? Omega is equal to 3 pi times 10 to the 7th. All right. And sigma, I'll just use sig, equals 1e to the minus 16th. I think that's everything, isn't it, guys? Right? And now if I go ahead and say what gamma is, would be equal to square root of 1j times omega times mu naught times the quantity sigma plus 1j times omega times 2, I'm just going to put 2.56 here, times epsilon naught. I think that's everything, right? And that's what I got. Do y'all follow me? Connor and Seiko, are you, or y'all see this? Okay, thank you. Yeah, Ashley. Oh, I'm assuming y'all follow me, what I'm doing here, right? Now, once I have that, that means alpha is what? Alpha is equal to real part. I'm not sure if it's just real or what the command is here of gamma. Let me see if that's it. It may not be. You could, and then, yeah, it is. And then beta is equal to the imaginary. Hope that's imaginary part of gamma. Yeah. Got me on that? So I have alpha and beta. Now I can get the phase velocity if I want. It would be omega over beta, right? So that would be the phase velocity if he asked, right? You with me, everyone? Got phase velocity, and he wanted h. Now, technically, h is equal to 1 over 8. By the way, I didn't get eta. What is eta going to be for this one? I'm going to use n. It would be what? Square root of 1j times omega, right? Times mu naught, it's non-magnetic, right? Divided by sigma, right? Plus, sorry, plus 1j times omega times, was it 2.56 epsilon relative times epsilon naught? Everybody agree with that?
Could you just do j times omega times mu all over gamma?
I'm sorry, say that again.
Find eta. Could you just do j times omega times mu over gamma?
But gamma and beta are interrelated, right? Gamma
so
is
you-
alpha plus j beta, right?
Mhm.
All right. This is the way you always get it. You go to the fundamental that has to do with the intrinsic parameters and the frequency, always. Intrinsic parameters are like epsilon, mu, and sigma. Frequency is omega. You got me, everyone, guys? All right. Now, once we have this, if we wanted the H field, and here I'm going to get this out of the way. Oh, thank goodness. All right. I'll leave it. If I wanted the, since I've got those values there, if I want the H field, and I have the E field, right? I have the E field phasor would be equal to 10, and then it would be E to the minus J, or I'm sorry, it would be 10 times E to the minus alpha. I forgot what alpha was. It's small. Let me do it this way. So if you look at this, alpha is this right here. Oops, sorry. That's eta. Alpha is this. It's extremely small. Do you all see that right there? So if that's alpha, whatever that is, I'm just going to leave it as alpha. E to the minus alpha z times e to the minus j. Now beta on this one is actually equal to, right here, is 1.59 about. Do you all see that? Guys?
Isn't it 15.9?
Oh, yeah, I'm sorry. 15.906. Yeah, you're right. I'm sorry. So this is going to be 15.09. I'll leave it as that. Z, right? It's in the AY direction, right?
Dr. Baginski, can you move the octave tab, please?
Yeah, yeah, I can. I'm so sorry. All right. In other words, I didn't put alpha down there. It's very small, but that would be E, right? just looking at this, the vector direction of propagation is what? Can you see it?
Is it Z?
Isn't it Z, guys? Everyone, take a look. Hang on, guys. Jack, you see that? Ben and Ashlyn and Connor, and y'all see that right there? It's just the the only thing I'm doing is looking right here. It's got 15.09 in front of it. It's got a minus J. It's going in the AZ direction, right? Agree? All right. That means this is equal to AZ. Now, if we want the H field, we've got the E field. We've got beta and everything. It depends if we want to express it as a phasor or time varying phenomena. But to get H, the only thing we do is take 1 over eta. Now, the thing about eta is it's complex, but the angle is about 0. You got a real part that's, I don't know, 16 orders, 17 orders of magnitude larger. For all intents and purposes, it's just the angle there is 0. So it's 1 over eta. Then you're going to have e to the minus, or then you're going to have e naught here. So e naught is 10, right? For this problem, over eta. I'll put in the value of eta is about 7.4459, but we'll put that in there in a second. I can put it in now. So it's 10 over 7.4459, right? That's going to be the magnitude. Then you're going to have e to the minus alpha. I'm just going to leave alpha alone. It's very small. And then e to the minus j, 15.09z. There's more numbers, but that's good enough. And then we have to get a unit vector in the direction of propagation. Now, I want you to watch this. So technically, h is equal to 1 over eta, unit vector in direction of propagation, crossed into the E field. Well, when we look at this, the 1 over eta is a scalar. And then when I look at the rest, the unit vector in the direction of propagation is AZ. The E field's unit vector is AY, right? And then you would have, of course, the scalar point here, E naught e to the minus j beta z. What is going to be AZ crossed AY, anyone?
Negative AX.
Right, minus AX. So this is going to be in the minus AX direction. Y'all follow me on that? You guys that are hanging out, Ben and Ashlyn and Sacred, with me? How many see it? Okay. Y'all see it? Okay. All right. Now, this is what I didn't do the math here, but we can do that in a second, right? Can't we, guys? We take a look at what he's got. This was, what problem was that again?
It was a
Drill.
drill 6 point.
Sorry. Get rid of that thing, yeah. Now, if you look at the drill here, you're going to see that his H field is minus, and he's got minus 42 milli, so this is going to be minus 0.42 actually. And it is in the AX direction, so you're right there, Jack, right? It's got the same cosine phenomenon. We know what beta is. We calculated beta. And he's got beta over here is 0.5. My beta, where's my beta? Is, I got 15. So I'm not sure if that's wrong or right. That might be incorrect. But the way you get it is the square root of j omega mu times sigma plus j omega epsilon. That will always be the way. He may have a wrong answer here. So if you don't get that, don't worry. And my alpha I got is I got a different value than he did. And I'm not sure, he may have made a mistake here. The frequency was 3 pi times 10 to the 7. There's something, the procedure I did is correct, but he may have something wrong mathematically. And I mean, he may have made a mistake here, and it does happen. I can check on that, Jack. But you follow me the way I did it? Any other questions, guys? You're probably ready to break out of here. Go ahead, Glenn.
On page 325, equation 6.32.
325, did you say?
Yes.
Okay.
Equation.
Hold on. 325 equation, say it.
Oh, it's 6.30.
Hold on. 325, 6.30. Okay, got it. Right here.
So when we're trying to find eta, that's the equation I just
Wait.
said.
Can you talk a little closer to? I'm hearing a lot of wobble, like a. Say it again. This equation right here?
Now, maybe. Yes, that equation.
Using that to
Which equation?
I was using that to find
This?
eta.
This?
Yeah, can you not use that to find eta right there? And I guess in the problem you can't do it because
you can use this to find eta, but you said beta before.
I'm sorry, I was saying eta, but the mic might be messed up.
You can say, sure, you can use it, absolutely.
Okay,
right,
so
go ahead.
in the problem, that's what I was asking if we could use it.
Yeah.
But okay, cool.
Absolutely.
I'm trying to remember where I even said that, but it's okay.
Yeah, you can use that, absolutely. The problem is gamma requires a calculation most of the time, so it's easier to just do it right here. In my opinion, okay?
I see.
Now, I'm going to give you some more. This is the thing that will save you a lot. Oops. Let me do this. Get rid of this thing. Let me do it this way. See those things I circled right here? Both of these two things require you have a direction of propagation. Remember how I showed you to calculate it, okay? Tell you one other thing since you guys, I've got the last four. Thank you for holding on. When we're doing propagation through dielectrics, I need to spend a little time on epsilon double prime. Now, in your EMAG 1 course, you should have been exposed to that. That's called the complex dielectric constant. Do you remember that epsilon double prime and mu double prime business or not? It has to do with loss. We'll talk about that. Don't let that give you any heartburn. You see 6.52 here, these formulas? I don't ever use them. That's an approximation. You have calculators that'll take it out to 6, 7 digits, right? Just use your calculators to calculate gamma and you get alpha and beta. Don't worry about this stuff. I don't use it. Nobody does. You follow me? He put it there. When he talks about low loss dielectrics, I'll talk about that in loss tangent. Propagation and conductors we'll go over, but we're going to go through and sort of take care of everything in this chapter thoroughly. But what I want to do is present everything in a way that it shows the linkage between E and H, between eta and gamma, and alpha and beta, and how you apply N power in all the situations, and I'll do my best. Now, any other questions about the homework, guys? Ben, you're up there in Huntsville, right? No?
I'm in Auburn.
Oh, you're in Auburn. I'm sorry. I thought I had somebody in here that was sending me messages. They were you're remote, aren't you? Or am I?
I'm remote.
That's all I need to know. No more. But I think maybe I don't have one person in Huntsville. Never mind. Anyway, no matter where you are, I hope you got this. Okay. William, did you have any other questions?
No, that was it. I was just like, I crossed it out in my notes. I was like, oh man, I like that formula. But yeah.
No, use it if you want it. Nothing else, Jack? I've had you for at least one class. You had me for
I had you for signals last.
Well, signals is a much more abstract type of course. This is more, you can visualize a lot of it. Any other questions before breaking off, guys? Do me a favor, be safe. Keep me informed of any kind of things that I need to know. And do we have a GroupMe page, William, or what do we have going right now?
Yes, we have a GroupMe page.
Did you Did you send
I
me,
put-
or did you put it in OneNote or not?
It's in OneNote and I posted it on Canvas as well.
Let me take a look about OneNote, and I appreciate you doing that.
Yeah, no problem.
I don't think I got on it yet. Has anybody else here got on the?
I've seen the link. I don't know if I've gotten in the group me yet, but I'm gonna sign off. Thank you, Dr. Baginski.
All right, take care, guys. I'm gonna hop on there if you don't mind.
Mhm.
All right, that's the YouTube. This is GroupMe, right?
Sorry. Yes, the GroupMe was the bottom one, the smaller one.
No, all right. Now I'm gonna join, if you don't mind. If you don't want
Yeah,
me in
sure.
the group, I'll stay out. What does it say? Did you all send me? Oh, never mind. I get a code on this one too. I hope I don't have to do this every time. What does it say? Your GroupMe pin is that. Yeah.
I'm gonna head out as well. Thank you, Dr. Baginski.
What's that? Okay, it's all right. Take care. Be safe, guys. Take care.
Mhm.
Hang on for a second, Wayne. Let's see. how
Yeah,
it goes.
it said that you just joined.
What is this chat business? Screenshot. Oh, that's you for me?
I don't. Oh, you're talking about in the chat. Yeah, I sent you a screenshot of the Zoom. That's what mine, or of the OneNote. That's what mine looked like
Okay.
of the solutions.
Okay. All right. Hang on
Mhm.
here. All right. So what does it say here? Email for. Did he say during the first class? Okay. That's taken care of, isn't it?
Mhm. Yeah.
Okay. So I guess we're okay, right?
Yeah.
Nothing.
Mhm.
I'm just going to say
Yeah,
one
I'm gonna
thing.
head off as well.
Yeah. Be safe.
Have a good weekend. Go
Hey,
back.
can you do me one favor? If somebody sends something there, send it to me. All right, take care. I'm done, Jen. Jenny? I'm done, hon.